Hey, what's up, guys? This is Cheng here again. So this time let's take a look at today's daily challenge problem number 902. Numbers at most n given digit set. So this is a very interesting hard problem because this is a more like it's related to the digits, and it also asks you to use the DP concept to solve it. Basically, this one is kind of like a DP with digit for the digits, so that's kind of unusual. All right, so you're given an array of digits, and you can use you can use any digits as many times as you want, and you can write those you can write them in any sequence. The only constraint is that you need to find the numbers you write has to be equal or smaller than than this integer n here. And it asks you to return the number of positive integers that can be generated, right? The total the total number of positive integers that can be generated given this digits array here, right? Whose value is equal or smaller than the n here. And there are some examples here. So the first one, like the example, the 20 here, right? We have a 100 equal is a target, and we have 4 digits here. And then we uh, we have 20 total possible numbers whose value is smaller than 100. Okay, and here we have, yeah, I mean, this one is pretty big. That's why, I mean, similar, but we have a much bigger output here, right? So on and so forth. Yeah, and here are some constraints here. All right, so given these two parameters, how can we approach this problem, right? So I mean, to solve this problem, we have to think it in we have to split this problem into several small some different scenarios. So the first scenario is what? The first scenario is that, as long as the total numbers, as you guys can see, so the numbers could be from one, let's say no, let me change this one to big N here. Okay. And then we have since we're going to I'm going to have a string equals to a string dot n, right? And then I'm going to have a n equals to the length of the n string. Okay. So let's say we have the total target digit is n, the length is n. So for 1 to n minus 1, right? Oh, by the way, and the digits is from 1 to 9, so which means that we don't need to worry about the leading zeros. Okay, so anything should be a valid digits. Okay, so okay, back to here. So let's say the total length of the target is n. So which means that from 1 to n minus 1, we can use any number for each of the digits. Let's say the n is equal to 4. So which means that the length from length 1 to from for length 1, 2, and 3, we can use any digits on each of the digits, right? So which means that what? So let's say the digit is this 4 number. So with all the length equals to 1, right? How many digits options we have? We have 4 here, right? Right, because we can put either of any of these numbers at this one digit. That's why we have 4. How about the 2 here? So let's say we have 2 digits, and when we can freely use any of the digits. That's why we have a 2 to the power, 4 to the power of 2. So because on each digit we have 4 options, and since we have two total two digits, that's why we have 4 times 4. Same thing for 3, 4 to the power of 3. Okay, so that's the easy case where whose length is smaller than the n, right? And so I'm going to write that real quick here. So since I will just talk about that, so for that, what do we have? We have let's say we have an answer equal to 0, and then we have for I in range of, I'll just remove this part here. So in range to what? 1 to n, right? So this is from 1 to n minus 1, basically, and the answer is what? The answer is like the length of the digits, right? So let's define the length of digits. Digits, I, I'll just call it the digits n here. So it's going to be the length of digits. So here we have the length of digits to the power of I, right? So that's the length smaller than n, right? Cool. So that's that. That's the easy case. And the more difficult part is when the length is the same of n here. For that, we have to consider the the answers digit by digit. So what does it mean? It means that let's say the target, assuming the n is like 2, 4, 6, 7, 8. So this is the n, right? And so what I mean by consider the digits one by one, which means so for this one we need to define like a dp here. So the dpi, so the dpi means that from from i to from i's digits to n's digits, assuming the from i's digits to n's digits, like what is the total positive numbers integers by given these digits whose value is smaller than this part. Let's say we have this is I. Let's say this is I, and the dp means that from the current i's location to the end, what is the total count for the positive integers whose value is less or equal than this part. Okay, and to calculate that, there are like two cases. Actually, there are three cases. So the first case is like this. I mean, basically we'll try each of the digits here, right? So at this location, this is n, right? So this is n. And so we're going to try each of the digits. So when we compare with the current digits of this n here, and basically there are three cases, right? Scenarios. Either the current digit is smaller than this one, or equal than this one, or greater than this one. So whenever, let's say the current digit is smaller than 6. Let's say the current digit is 2, right? So what does it mean? It means that assuming the current digit is 2, it means that we can freely put any digits on on this two position, right? So which means that we can like we can just use this formula to calculate this case, which is going to be the length of the digits to the power of, in this case, is 2. Yeah, but we're gonna have like so it's gonna be a n minus I plus 1, something like that. So that's the first scenario where the current digit is smaller than 6, right? Because since this one is smaller than this, so it doesn't really matter what we have here. So that's the first case, right? So that's and the second case is equal, it's 6, is equal to this one. So whenever the digit is the same as this one, so what do we have? We have basically we cannot freely put anything we cannot freely put any numbers here, but it happens to be that, since this one the same, so it happens to be the DPI. So the DPI will becomes what? Will become the DPI plus 1, right? Because the DPI plus 1 is the total valid count starting from here, which is exactly the equal case for us, because the what because whatever we have in DPI minus 1, it will be the same in this DPI here, right? Because the current digits is the same, so we're, we're counting on the DPI plus 1 to tell us how many valid numbers we have. And the third scenario is like it's 8. Let's say for example it's 8. So when it's 8, of course, this is an invalid case because this 8 is already greater than the 6, 7, 8. It's greater than 6, which means that there's no more digits, right? That can start with 8 that can satisfy our condition here. And yeah, and we just keep going backwards, as you guys can see here, because the difference for this DP is that we have to going backwards from the end to the start, because from the current digits we have to rely on our digits on the right side, and in the end, when we're at 0, we will have and when we have at 0, the DP0 will give us the total count, right? For the length for the numbers whose length is equal to are the same as this length here. And then we just need to accumulate that, summarize that with this answer, and that will be our final result. Cool. So, and all right, so let me try to code this part. So now handle the length equal to n, right? So like I said, we need to have like a DP here, at the beginning, the DP, they're all 0 because we're storing the valid count, right? Starting from here to this is from I to n, right? And for I in range of the n minus 1, minus 1, minus 1, right? Like I said, we need to start from the end. And we try each of the digits, right? Because we have to try it. Because for each digit, we have a different scenarios here. For each digit in digits, so the first case is if the digit is smaller than the n string dot I, right? So if the current one is smaller, we can just accumulate. We have to use digits n to the power of this one, similar like this one, but we have to calculate what's the remaining digits, right? So the remaining digits is n minus I minus 1. Okay, because the n is the length and the I is the index. That's why we have to also do a minus 1 to get the remaining number of digits. Okay, and so for the remaining digits, we can freely use any of the digits, right? All right, that's that. So else if, right? Else if the digit is equal to the n string I. So in this case, like I said, the 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 value will be the same as the dp I plus one. Okay, because the current one is the same, and we have to just use whatever we have from dp I plus one. And then in the end, we can simply return the dp0, right? And then plus the answer, because the dp0 will stores the total result for the length that's equal to n. And actually here there's like small edge cases we need to be careful, because we're starting from n minus one, and we will do a dpi plus one, So if the I is equal to n minus one, and if we do a n I plus one, it will be out of the boundaries. So that's why we can just simply do a check. If the we only do a dpi I plus one if the I is smaller than n minus one, right? Else, else it's just one, right? So this is the case where the digits is the same as the 2, 4, 6, 7, 8, where this is the digits, the first digits, and the current digit is 8, which is the same as this one, which means that it will be plus one, right? That's one count. Yeah. Or we can just do a padding here, instead of initialize it to n here, we can do a n plus one, and then we set the last element to one. I think either way is fine. Hmm. Okay, so I think that's it. Let's try to run the code here. Okay, accepted, submit. All right, cool. So it passed. And let's see what's next. Yeah, so the time complexity, right? So the time complexity is is what is the so the digit size is n, and this one is 10 to the power of 9. But we're getting, so actually the time complexity is only the length of this n, which is what I think the length is log n, right? So that's the length of this n here. And we have a for loop of the length here, and another for loop of this one. So and the digits here is, yeah, so it's only a constant, right? So it's bounded. So here we have up to 9. That's why the total time complexity is still the length of this n, which is the log n. Yeah. And the space complexity is same thing, because we have a dp here. That's why the space complexity is also a O of log n. Yeah. All right. So just to recap, right? I mean, so for this kind of like digits related problem, it's always, I think it almost always will relate to comparing the current digits, because especially when you need to compare if the digit is smaller than target or greater than the target. So based on the current digits, you will have a different options like what we have here. So in our case, I mean we calculate the easy scenario first, which is the length which is smaller than the target than the n here, which means that we can freely use any of the digits on any of the numbers on any of the digits. That's why we have this total numbers. And then we'll use like a dp to help us accumulate the case where the length is the same as the n here. So for this case, we have to we have to loop through each of the digits, because based on based on who is bigger and who is smaller with the current digits, we will have a different accumulated count here, right? So for the digit which is smaller than the current numbers, right? We can just freely put anything on the next few numbers. And the reason we're using the DP here is only for this case. For the case when the digit is the same as as the current number. In this case, we have to use the count that we stores in the previous DP, which is the DPI plus one. And of course, for the last case, we can simply ignore that. And then in the end, we simply just add two values together, and that will be our final answer. Mm, yeah, I think this is a very interesting DP. It's not like a traditional DP, or this is just like a DP with the digits. I hope you guys enjoy watching this video, and I'll just stop here. Okay, thank you so much for you guys to watch it, and stay tuned. See you guys soon. Bye bye.